Okay, hi guys. Thank you for coming to this talk. What we're going to try to do today is telling you a bit of how we got to ChatGPT. That's what everybody's talking about now on AI. And it's just going to be a bit of history and a bit of explanation on how it works behind the scenes, right? So let's get to what's an AI. I guess that everybody knows here that or has an idea what an AI is, but you have to think and you have to know that an AI is not an implementation or an application or a specific thing. It's more of a computer science task of investigation. It's where you try to investigate the what is the field of investigation of the computer science of AI and artificial intelligence is the development of machines that try to perform tasks that require human intelligence. But not only intelligence is the way we think, but it's the way we interact with the world, the way we see, with the way we talk, the way we listen. So right now you have a lot of implementation of algorithms that maybe try to synthesize voice or simulate or try to transform an image into interpretation, or like ChatGPT, like they interpret the text and they talk about like a human, right? And right now the human intelligence is also being like, you have to define what is human intelligence. Recently there was a paper that was trying to talk about what is doing ChatGPT, and the conclusion they got is we don't know if it is really now intelligent or not, because we have to redefine what is human intelligence. So not only you have a computer program or a computer implementation of intelligence, but you have to define what really intelligence is, right? And right now, you know, there is a really big hype about ChatGPT and all these large language models, but artificial intelligence have been in our life for a long time, and we have been using it knowingly or without knowing. When we use Waze, when we do Netflix or Spotify or whatever, there is a kind of artificial intelligence there, being machine learning or neural networks or whatever the algorithm is. There is artificial intelligence behind it. So it's in our life, and it's have been here for quite a long time. So let's talk a little bit about the history and where it all began. It all began, I mean, the artificial intelligence field was defined or began in the late 40s after World War II, when the digital computer was invented. And right here we have a timeline that has some random, I mean, not random, but important milestones on artificial intelligence. It's not complete. It's just some that I thought that were important. Like in 1950s, the Turing test was invented by Alan Turing, right? Everyone knows about him, and probably everybody knows about that. The Turing test is trying to trick a human into thinking that a computer is another human when doing a chat. And the other thing that was really important at that time, it was the development of the perceptron. The perceptron is something that we're going to talk about later, and it's super important on what we talk about today about ChatGPT, but let's leave it here. You have to know that it was invented in the late 40s, and it was first implemented in the late 50s, in 1958, I think. And then we have the first robot in a factory working without human control. I mean, with human control, but it was working autonomous and General Motors. And Eliza, it was one of the first chatbots that it was trying to simulate psychotherapists in, I don't remember what university. And what's important here is that there was, as you see, it began in the 50s, but there was a really long time during the 70s, 80s, that is called the AI winter, because there was such a big hype during the 60s that this was going to be super useful, that it's going to solve a lot of problems, but the results were never there. So everybody lost interest and there was no money on it. So it was really difficult to make new improvements. It doesn't mean that during the 70s or the 80s, there wasn't anything on this field, just that there wasn't money. So most of the work was being doing in universities and not really big implementation of all this. During the 80s, what most of the improvements were on expert systems, that such are systems that works on rule-based. Imagine like you go to a mechanic and you bring the car there and the mechanic says, okay, what's wrong with here? The engine makes this noise. Oh, with that the noise, I think that the problem is here and I see there, and it's just a continual set of rules that you can program on a computer. That's an expert system, right? And most of the improvements were on that kind of systems. And we see here that the most important of that was Deep Blue, that is an expert system, that IBM programmed a computer to be that on chess, one of the champions, I think it was Kasparov. And right then, it's when we start to see a lot of improvements on applications in real life. And we start with the Roomba and Siri and all stuff that you started seeing on your daily based life. And we got to this point where we are now that after a lot of work during the last 20 years, I think, that you have a lot of machine learning algorithms, a lot of neural network algorithms that were implemented on real life. They were not just on universities, on studies, they were on technology. We have like assistants, Alexa, Siri, Google Assistant. They have a lot of things that we interact day-to-day basis, right? And we get here to ChatGPT, that is like what we know now, that is like super impressive. And we don't know what's going to happen next. It might be that we start seeing really fast development, or it might be that all the hype turns into nothing and we may come to another winter. We don't know really, but we hope that it's going to be an improvement, right? So that's for the history. That's nobody cares about this, but it's nice to know. So when we try to think about how a machine learns, or what is that a machine learns, we have to think that there is a difference between learning and giving instruction, right? When we code, when we develop a program in any language, whatever language you like, we just giving instructions at high level that are going to be transformed into low-level instructions that is going to be do this after this and do this if this. It's just a set of instruction and it's not learning, right, really. When we talk about machine learning or computer learning or whatever you think about a computer learns, is just trying that the computer determine a set of weights or a set of processes internally that giving a certain input is going to give us certain output, right? So for this, we have two different methods, supervised and unsupervised. Supervised, you need a lot of information because it means that you have the input and the desired output tag. So like, I mean, imagine on a visual interface, you have a photo of a cat, you know that it's a cat because you tag it as a human, and you give that information to an algorithm, and that algorithm makes a lot of math calculation and decides that when giving this input, I'm going to give you that is a cat. This is supervised. Unsupervised, you give the same photo of the cat, but you don't tell that it's a cat. And the algorithm is going to try to find relationships and going to try to find information inside that picture or whatever you give it, and it's going to give you a result. It might not be the one you want to, but it's going to be the result you get without that tagging. It's just two different methods of making the machine learn. And that learning is just a set of weights or a set of black box. You don't really know I mean, you can know the numbers, but you don't really care. It's just a set of information get in and a set of information get out. And in the middle, it's just what the algorithm decided that's going to be the process that is going to be the output that you need. So that is a machine learning. It's not a set of definite instruction. It's just let's go with the same. It's what you get when you use this machine learning algorithm is a set of weights that decide the output according to certain input, right? So let's go a bit more about, I'm going to let JC talk about what is ChatGPT and how it works, right?
Okay, guys, thank you, Fede, for the history lesson and the explanation on how machines learn. And so with that in mind, we are going to put GPT under the microscope, right? And we are going to try to see what makes GPT tick inside, right? And what is built of. Right, like we heard that Fede told us about neural networks and the perceptron and some kind of models that we all hear those words in the media, right? But we don't know what they are and what is truly behind all of this, right? Like we know what the world is made of, like atoms and whatever we see in our primary classes and secondary classes, right, in biology, physics, and whatever. But here in this thing that we are talking about intelligence and new beings and what is intelligence, we are all seeing this black box that is ChatGPT, and somehow it's returning this text that is really human-like, but what is really inside there? Is there another person just writing all the outputs, or is it really a machine doing it? So we are going to try to shed some light on that. So we are putting here the logo of ChatGPT under the microscope. So ChatGPT, let's go. So just putting the first magnification here, we see this kind of thing that has a lot of parts, right? But for me, it's not clear enough yet to, I mean, I don't have enough information here to be talking about this, because we have to explain every step right here, right? So I will try to go as deep as we can. Here we have the transformer, so I want to know what lies behind this. And yeah, the transformer this is the transformer logo of the TV series, right? The cartoon. But actually, this is a set of apparently some balls and some calculators and some distribution here. But we are going to focus on these things that apparently are called neural networks. We are going to go one layer, one magnification more deep into this with the microscope, because apparently these neural networks is built on by these spheres, right? So let's go in this at this level, and what we have here is what Fede told us about just some moments ago. This is the perceptron, right? This is some kind of at least at this some level is some kind of black box where we put some input and it and an output comes on the other side. This was actually developed to mimic the way that human neurons work, right? So you have some input in one hand and the output on the other hand. Just keep that in mind. That is the way that it was taught at first. But let's try to see how this thing, the perceptron, works. This perceptron actually is the building block, like the principal building block, right? The main building block of the neural networks. And what it is just this thing that you have here. In one hand, on the left hand side, you have the inputs. And when we talk of inputs at this level, we are talking about numbers, right? You have some numbers that then go through some weights. We are going to explain what that means in a moment, but those numbers go through some weights, and then you summarize that weights and inputs somehow, and then you do a little bit more of math, and then an output comes, right? So you have several inputs at one side and one output at the other. So this is really basic, as you can see, is really basic, and we are going to try to see what is the math behind this thing. This is not that complex. It's just this calculation. It's pretty simple. It involves just basic math, where you have a previous output, right? This said thing, and then you might multiply the input value in one of these inputs by the weight, right? This is just a common multiplication and then a common summarization. Again, this is, for now, is really basic. Then the summarization and multiplication that you get in this said variable is passed through this sum and activation, right? The sum part is the said thing, and then the activation will be the other two instructions that we have at the bottom. If that threshold, that 0.5 number that we have in there is called threshold. It's the activation threshold, you could call it. And this is one of the ways that this could work. Actually, there are several more, but we are going to try to keep it as simple as possible. So if the set value is above 0.5, and the output of my perceptron is going to be 1. And if it's below 0.1, the output of the perceptron is going to be 0. So according to the inputs and the weights, we get 0 or 1 at the output of the perceptron. Okay, this is really pretty, right? We can see it with numbers, so you get a clearer picture. Here you have these weights inside of the perceptron. Just keep in mind that these weights is not something that we can really see. Let's say that I give you a perceptron, you wouldn't see the weights. You will just see the inputs, that you have 2 slots there to put the A and B numbers, and then an output will come on the other hand, right? And here you see the process where we multiply both of the inputs by their weights, and then we have 0.6 that, as we said before, if it's above 0.5, it's going to return 1, as we see here. Okay, so this is the way that you use, right, the perceptron. But we were talking about machine learning. How does the perceptron learn what to output on the other side, right? Okay, that is what we are going to try to explain right now. What you need to do to make the perceptron learn whatever you need it to do is to have some samples, right? This is a supervised, let's say, way of training, where you need some values for the input and an expected value for the output, right? So whenever you feed those values at the input, and then you compare what the perceptron outputs with the expected value that you have. And then you subtract those two values, right? And then I'm going to display here 2 functions. Don't be scared. I mean, they are really simple, and it doesn't matter what they are, right? I mean, what you're seeing here is that we multiply that difference between the expected value that we wanted and the value that we got. We multiply it by something called the learning rate, and this is just a ratio that we want the weights to shift on, right? And what we are doing here is to modify the weights according to the error that we had in the output, right? So we update the weights in order to make the perceptron learn. That will be the idea. Okay. So going a little bit further, let's go back actually, right? With our microscope. Now that we know what perceptrons are, that these are these things that take some inputs and then an output comes on the other hand, we can put those perceptions together and form this thing called neural networks. And neural networks are, at its basic form, I mean, there are some other types of networks and whatever, but we are going to try to keep it basic here and go with the most basic ideas around this. So a neural network is just a combination of perceptions. We can just think that in that way, right? Where we have these layers of perceptrons that will process the inputs, and then we have several layers in the middle that are hidden from us, right? Because we don't interact with them. They are just there to connect the input layer with the output layer, and then we have an output layer, right? And now what we can see, let's go a little bit further in this diagram, right? Let's explode it a little bit. And what we have is some perceptrons here and the first layer, and then we have two hidden layers, and then we have an output layer, right? The first layer can take several inputs for each one of the perceptrons. And then the layers in the middle just connect all of those layers. And then at the output, we are going to have one output for each one of the perceptrons, right? And of course, this is all pretty, but how do we train this, right? Because, I mean, we know how to train a perceptron, but we don't know how to train this. Because if we think about it, what we have, right? Because as I said, how we interact with this network is through having some inputs and having some outputs, right? And if we want to train it, we need some inputs and some examples and the output for that input, for that given input. So whenever we try with another input that we don't have the output, we can use it, right? So the way that we train this is by some algorithm. I mean, there are several algorithms, and this was actually one of the key developments in the 60s, where they applied calculus, right, to train these networks. And the way that you train this is to apply the same principle that you do in the perceptron, where you update the weights, right? But you have to do it for all of the layers and for all of the perceptrons, okay? So what you do is to compare the outermost output, right? And compare it against the expected value for that output. Then you calculate that error, and then with that error, what you do is a process called error propagation. And keep in mind that what you are propagating is not the error per se, but actually the corrections in order to apply corrections to the weights in the previous stages of each of the perceptrons in the network. Okay, so this process involves calculus and derivatives and minimizing functions. That doesn't matter. I mean, what we need to understand is that we have some expected output. We compare against the output that the neural network gave us, and then we calculate the error that we have, and then we propagate using some kind of function and apply that propagation to each one of the weights that we have inside of our network. Okay. So when we call a model, right, when you hear the word weights inside a model, I mean the weights of the model, etc., it's those weights inside of the neural networks, the weights that have been trained in some piece of data that you have in the input and the output, and then you have this arrange of numbers, this big array of numbers that there are several millions of numbers, you could say, depending on how big the network is. Those numbers are what actually the network is, right? I mean, the network is not just the numbers. I mean, you also need the way that those numbers are connected, right? But that's the idea of the neural network. Okay, so let's go one magnification lower, right, with our microscope. What we saw is the perceptron, and now we saw the neural networks. And now here we are seeing the transformer network. And keep in mind something. Up to this point, we were talking about things that handle numbers, now, and now we are going to start talking about things that handle some other types of data. Sometimes some numbers, sometimes can be text, sometimes can be some kind of encoding and other types of values, right? So in order to put inside of the networks those values, right, that are not numbers, because the neural networks only process numbers in its purest form, right? We need some dictionaries and also algorithms, just regular algorithms, to transform the type of data that we get in the input to something that the networks can use, right? That's why we have those calculators that will be the algorithms or the calculations that we need to apply to the inputs, and also a dictionary, because sometimes you need to transform some given value into some number using a dictionary or a lookup table, okay? Okay, so let's go a little bit deeper into this transformer network. And again, this is one of the types of networks that there are. I mean, not every language model, for example, GPT-2 was based on some other type of network, but ChatGPT and GPT-5 and etc. it's based on transformer networks. As Fede said, this transformer network was invented by Google, I believe, in 2017, maybe before, but that's the information of the paper that we have, right? I think it's called "Attention is all that we need." Okay, and the idea behind this type of transformer, this type of neural network, is that you take some input, right, that you have lying there. It can be, at this moment, actually, there are still some kinds of numbers. It's not text, but we can think it not just regular numbers, but maybe an array of numbers or something more complex than just numbers. And then we adapt those numbers to something that the network can understand. And what you do with those numbers is to embed them, right? What you do is transform them in a way that the following networks are trained to understand, okay? And that's why when you hear embeddings, right, when they talk about embeddings and etc., it's because you are doing this transformation of the information so the network can process it later on. Okay, so that's the first layer. And then in the second layer, we have something called encoder. This thing is just built around neural networks. And these networks are actually chained together. They are not just one neural network, but several. And they work in a process, in a serial process, right? One works behind the other. And in this encoder process, what you have is two types of neural networks that work like the ones that we talked before, where you take numbers and then some numbers go at the other end. And you have two types of this attention of these networks. Something that I didn't tell you is that the network will do what it's trying to do, right? So you train the network to do some kind of task. Like you put some numbers in one end and some numbers on the other end to train it, right? Something in the input and you check the output and etc. You train it, and you train it to do some task. So an attention network and a feed-forward network that we have here in the encoder stage are two networks trained to do some tasks, and two different tasks, right? One is attention and the other is the feed-forward. I'm not going to explain what those do. Maybe Fede will shed some light on those, but what I want to explain is that what you do is to grab the information that you get in the embeddings, and then you apply these attention and feed-forward mechanisms and networks to make connections between the inputs that you have, right? And to add more value to the inputs that you have. Like, for example, let's say that you have several inputs. Let's go with text, right? You have several words. This encoder stage, what it's going to do is to add meaning to the way that those words are connected. Like because of the position or because of the exact word meaning, it's going to add more metadata to those words. We can take it in something in that way. And then what the decoder does, using the same types of network, but trained differently and arranged it a little bit differently, they will take all that expansion of the input that the encoder did and will try to lower it a bit and find find what it needs to generate, right? Using the input. I mean, it will compare all the information that it expanded in the encoder and also the input, and try to see what it can arrange that it works with the input. And the output of that decoder is going to go to this output layer where you apply some kind of algorithm and you create this distribution of probable outputs of this transformer network. Okay, so now at this network, we don't have like an input and an output. It's just like we had in the neural network. We get some input that is not just numbers, is something a little bit of a higher order. When we talk about LLMs in a bit, it's going to be a little bit more clear. And what you have at the output is just a distribution of possible outputs. It's not just an output, but a distribution of possible outputs. Okay, so let's crank our magnification a little bit lower, and we are going to see again the LLMs. Here we can see the transformer at the middle, what we were talking right now. And here we have here we can see that now we are just inputting text and outputting text, right? This is the large language model model of network. And the idea here is that this is what ChatGPT is based on, okay? So let's go a little bit inside of this. And what we have here is that we have this text input, right? That we have to process it. Let's say that we have some kind of a string that we want to process, like whatever you input, for example, in ChatGPT, like a sentence or whatever. And then you have to process that data, right? Because that data, as we said before, we cannot put it just in the transformer network or in a neural network, and then we get text at the other end. We have to process that into something that the transformer network can use. So the way that we do that is to, for example, split that text into words, and that process is called embedding, right? Like we said before, you have to do this at this stage also. For example, let's say that you have 3 words, you can split that into words. Some other kind of embedding is to split those words in some subwords, like syllables, for example, or you can also split them into characters, right? Then some kinds of algorithms applies, and instead of sending words to the transformer network, what you send is an array of numbers representing those words, okay? So what you do in the first step is to grab the text, process it somehow, and then you get numbers. And then those numbers, of course, those numbers are vectors, right? What we call vectors or arrays of numbers. But let's keep it simple. They are just numbers arranged in some way, and we send them to a transformer. We explain what the transformer does. So the transformer takes those numbers, and then at the end, we have this distribution matrix of the possible outputs, right? But with that distribution of numbers of possible outputs, we cannot do anything, right? We cannot build the text output yet. What we need is this decoding algorithm. And this decoding algorithm, what it does is to iterate over that distribution of possible values, and tries to build, right, the output of the transformer network, right? So using the distribution of values that the transformer network gave us, the decoding algorithm does kind of like a loop, right? And tries to guess what is going to be the next word. And of course, the process is not like, because the distribution is a distribution of numbers now, right? So it has to pick what is the next number, you could say, we can take it something like that, and then it has to translate that number into some kind of token, some kind of embedding, and then translate it into a word, right? And all of that is handled by this step of the decoding. Okay, so that's more or less how ChatGPT works, right? You have some text, it passes through these embeddings, then you have the transformer. The transformers uses algorithms and also uses neural networks, and the neural networks are built by this thing called perceptron, invented in the 60s, that uses just numbers and regular math to calculate these weights and etc. And then you get a little bit farther back, right? You go back, and then you have this decoding algorithm that grabs the possibilities that this transformer built, and then you build back the text. it seems really complex, but when you see it, right, all the steps, it's what you actually have is just numbers working there and somehow creating these text outputs. Oh, everybody's muted because I had to wait. Okay, so if anybody wants to ask any question, please feel free to unmute yourself. Fede, also, if you want to add something that maybe I missed.
No, it was great. I think your explanation was great. It's basically that, as you said, you enter something and you get something out, and it's just probabilities. It's not like magic in there.
Yeah.
Everything comes down to probabilities.
Hello. Hello, guys. Great presentation. I just have an example to add or to show how the embeddings work. There is a classical example with the words king. For example, you have the embedding representation of the word king, right? And it's some array of numbers. And if you subtract from the word king the word man, you obtain the queen embedding, the queen vector. So if you subtract from the king, you subtract man, you obtain queen, or if you add from queen, you add man, you obtain king. There are those relationships in the embedding space. That it's one way to
that is a great example because we didn't talk about that.
Yeah.
But embedding is not just a transformation of a word into a number. The embedding also includes relationship between words. So as Facu said, a king or a kingdom without queen gives you king, or it's because that embedding includes the relationship. So in the numbers or in the position, if you try to map it on a graph, you're going to have like the king here, the queen here, and kingdom, they're going to be related. So the numbers are going to be correlated also. It's not just a dictionary where you take a word and you convert it into a number. It includes like context or relationship between those words and weights, right? That's super important. Thank you, Facu.
Like the meaning, like the meaning of the words. For example, also embedding this of, let's say that you have a verb that is conjugated, that verb is going to be defined in the infinite form sometimes. And something that comes to mind when you said this about subtracting the king by man and then becomes queen, is the idea of summarizing emojis, right? We had a talk about some months ago from Valentina, I believe, that he showed how you can sum up some emojis and then a new emoji comes up. So yeah, that's pretty much the idea. I mean,
nowadays it's pretty analogous, right? Great.
Yeah. Thank you, Facu, for the input. Do we have any more questions? Maybe we left them speechless.
Every guy got lost on the math.
Yeah. We try to maybe make it as simple as possible. I actually wanted to, at first, some weeks ago, I wanted to build some kind of JavaScript code to train a perceptron, right? But yeah, maybe that was too much, right? We wanted to make it as simple as possible to everybody to get it without going deep into math. Like, for example, the backpropagation algorithm, you can, for example, show the equations, how you calculate that propagation of corrections to each of the weights. But yeah, that's not needed, right? What we wanted to show you is that behind all of this, behind all the content of ChatGPT, what you have is just some algorithms that do something, and then at the core of it, there are just numbers, and that is what neural networks are. So just an array of numbers that those numbers put it in the I mean, those numbers are really pricey, right? Because you have to really work hard to get those numbers in arranged in that way, because you need several hours of training that cost several millions of dollars, we can say, for example, for ChatGPT. So those matrices of numbers are really pricey.
Yeah, and also want to add that when you talk about the weights, that's probably something that everybody's going to hear when they release a new model, or we'll talk about Llama model or whatever. What is being released are those weights. It's the results of all the training, all those numbers that need to multiply the input to get the expected output. That is what's released in the model.